Okay, so this is the decision we were working on. We said that if we first wait to see or find out if it's going to rain or not, then we can make a better decision, right? So that usually, I mean, I'll discuss this later as to why in any system design or system operation, resolving uncertainty before you make a decision is always valuable. Which, I mean, it's not always possible, but when you can do it and then if time permits it, it's usually valuable. And then there's also techniques to find the actual value or how much money you should spend in resolving that uncertainty. And then the other point I was making is that when you do this sort of analysis, you're assuming what's called perfect information. And that's not necessarily always required. If you have imperfect information, then you need some knowledge about how good or bad that source of information is. So then we start talking about conditional probabilities. I'll touch upon that later in the lecture. So this is a better situation if we can resolve uncertainty before we make a decision. So the second simple decision problem right now, as you may recall, we were practicing how to draw decision trees. So we're not really trying to solve the decision trees. We're just trying to represent our decision situation using the standard view. So let's say I'm deciding on whether to buy a new car or a used car, okay? And the only aspects I'm concerned about are if the car breaks down and the cost of ownership, okay? So not how much you pay in the beginning, but more so is like, how much you pay in the repairs, right, when you own the car. So actually, it's better if you try drawing this yourself, and then we can go from there. So the decision is, so in this case, again, like, we make a decision before we have the uncertainty known to us. We make a decision, which is a square, and then we go to whether a new car or a used car, right? That's basically the decision. And then there's an uncertainty. Any ideas what that uncertainty is?
Breaks down or doesn't break down?
Yeah, it breaks down or it doesn't break down, right? So obviously we'll add an uncertainty node or uncertain node here. In both cases, it breaks down and it does not break down. And when it breaks down, what happens? You spend money to fix it, right? And if it doesn't break down, you don't have to spend any money to fix it. So that's how the decision is there for now, that if you buy a new car, it breaks down, then warranty covers repair. So that's a good thing about a new car, that you don't have to pay for it. Okay? Most car companies will warranty their cars. And if it doesn't break down, you have a reliable transportation. If it's a used car and it breaks down, you have to pay for repair yourself or repair the car yourself, I guess. And if it doesn't break down, you have reliable transportation. So this is a very simplistic model, and then this is what I try to do when I teach, is that I build complexity into a model, right? So now let's start with some of the things we're missing here that makes this a little bit more realistic. Any ideas? So how can we make this tree more realistic? Because right now it's just like, new, used, breaks down, doesn't break down, okay? But that doesn't really cover reality, so to speak, right? What is missing? What is the first thing that's missing? Okay, great. Yes, same thing, right? So these probabilities are different. So just because we drew two uncertain nodes does not mean that they have the same probability. Of course, in decision trees, in reality, we will add the probability number to each of these each of these arrows, that this has this much probability of breaking down and the other one has that much probability of breaking down. The next question I have is, which car has a higher probability of breaking down? Used? How many of you say used? How many of you say new? Well, yeah, it is not an easy question to answer. I mean, typically you can expect a new car to have less reliability issues, right? But then there's also this concept of infant mortality that you have some a lot of design issues or manufacturing issues are found in the first few usage periods of a vehicle or any system. So that's one thing that could skew the numbers. I'm still not saying that it'll make a new car less reliable. It'll just change. It wouldn't be as straightforward of an assessment. And similarly with a used car, maybe most of the errors have been found and fixed. So you may actually end up with a reliable transportation. Okay, so that's definitely the case. And then the other thing that we did not do in here was did not take into account the cost to purchase, right? We just said, of course, right now we're just practicing our broad decision tree. So it's not critical, but it's also good to know, like we're building into layers of knowledge. And then we'll say that if we have a new car, obviously it's going to cost more than a used car, assuming they're of the same type, the two cars. If the other car is a really luxury car, even the used may be more expensive than a new of the other kind. So those kinds of things are not built into this. And sky is the limit, right? We can make this as complicated as we want to. But the main point I wanted to make was that a new car and used cars will have different probabilities of failure, and so on and so forth. Okay, so now that brings us to the decision-making axioms. Okay, what happened here? Sorry. And before we talk about the axioms of decision making, we will spend a little bit of time talking about decision making frame. Okay. Similarly to any system analysis problem, any engineering problem for that matter, you have to have the proper frame for decision making. Frame means what are the things that I'm considering, what are the things I'm not considering. If you have a let's say a decision-making frame that includes everything, and that's the point I was getting at with the last one. You can go nuts with like adding layers of complexity. Okay, used car, this and that. Then you can say it's a multi-attribute problem. New car has more prestige. Old car does not have the same prestige. Old cars may be unsafe. New cars may have more features, and those kinds of things. So the more you put into your decision, you might think that you're actually improving the quality of your decision. For some few initial steps, yeah, you are improving the quality of your decision, but after a while, the analysis becomes so hard and you don't actually have those probability numbers, and then you start making ad hoc type analysis, or it becomes so complicated that you cannot fully analyze it. So a decision-making frame is the result of meta-analysis. We call it meta-analysis, meta-decision of what all we need to include as the essential elements of a decision. So we want to make sure that we don't leave anything out that is important. We also want to make sure that we don't add too much into our decision that has minimal impact, right? So oftentimes a proper frame will involve understanding of who the decision makers are. We need to know who's making the decision. And then later on, when we talk about decision utility functions, we will see that knowing who the decision maker is, what their preferences are, is really critical to making decisions, because no two people make the same decision. And that's one of the things that we do in decision analysis, that we capture your preferences. Means that one company is aggressive. I think somebody touched upon risk attitude earlier, right? So one company is aggressive, may make decisions differently. Two decisions, they may select option A, and then another decision maker may select option B, even though it's the same decision, just the preferences change. Their preferences, details to be included in the problem, how many different possible alternatives you want to consider. And like I said, possible decisions, possible outcomes. When we flip a coin, we don't always consider that it can land on the side. You can include it. It'll have a probability of 0.00001, and you could carry it in your calculations, but you're just doing it. It's not going to change anything pretty much. And then uncertainty, right? What sort of models you will use. And then again, it's like certain things you could consider that they're likely, unlikely, or very low probability, or what kind of model you would use. You could go nuts trying to collect data and finding the best probability distribution fit that you can find, or you can say, you know what, for this kind of, let's use a more well understood distribution. So all those decisions go into problem framing, and then it's an art and a science, as we say. You could come up with I don't think you could really come up with a scientific way of deciding the frame. It's something that you, as a decision maker, as a systems analyst, as somebody who's actually analyzing the system, has to make a decision on their own. What is reasonable, what is not reasonable, and what am I missing something that's too critical? Am I adding too many details? That's an art as much as it is a science, right? So, and many times you can do these kinds of things iteratively. You do it once and you say, you know what, we didn't consider these options or these decisions or these uncertainties. Let's do this. Or we have more data now, and then we can redo the probability distribution. We can redo our uncertainty models and go from there. Okay, so with that aside on problem framing, we come back to decision analysis axioms. Okay, some basic set of rules that we all agree with and we accept or expect our decisions to follow. Okay, so axioms are statements. You already know this from our earlier discussion, that axioms are statements which cannot be proven rigorously, but are mostly hard to dispute. Okay, so you can't be at two places at the same time. Okay, well, I don't know if I can prove it. I don't think I can go everywhere and see if there's no other copy of me anywhere else, but we're just taking it as face value, right? That you can't be at two places at the same time. Right? Companies should work towards improving their reputation. There's really no rule for that, but then companies have realized that if they use this as an axiom, they generally do well in the long term. Okay? So decision analysis is axiomatic, and these axioms will lead to a mathematically rigorous way of making decisions, as we will see. So, benefit of an axiomatic approach is that it helps us come up with methods to make decisions, right? And axioms is something that, like I said, there's no proof, but we all should agree. If anybody in this room or any discussion has a problem with an axiom, you should not proceed, right? We should resolve that problem, because that's the foundation of any theory, okay? So it'll help us come up with a method to make decisions, and then it will help us defend a decision. So many times, if you make a decision that decision analysis says bad, I can backtrack it and I say, you know what? Essentially, you are saying that you want a higher probability of failure. But you said that you want a lower probability of failure. So we can backtrack, and then, so that's the thing with axiomatic methods. Okay, so it was first presented in the form that's similar to what we have now by von Neumann and Morgenstern in their book Theory of Games and Economic Behavior. I think most people here are ISE students, right? Industrial and Systems Engineering students. Yeah, everybody. Huh? Right. Industrial Engineering and Management Science students. So all of you should have a copy of this book. Okay, it's like a Bible of game theory and even decision analysis. So basically, von Neumann was a mathematician, a great mathematician, contributed to a lot of different fields. They came up with an axiomatic approach to decision making and presented it, arguably for the first time, in almost the form that we use now. So the same axioms or some slight variations of it. I mean, you can see many different authors presenting it in different ways, right? So here's a list of some authors that have presented it, the same axiom slightly differently, But it pretty much leads to the same thing. It leads to the utility function driven way of making decisions. So, and the axioms imply that every rational decision maker should maximize the expected utility when making decisions, right? So there's a merit function or a performance function, which is what we call a utility function. And then every rational decision maker who agrees with the axioms will maximize the expected utility in each decision, and that will lead to the best decision possible. Okay? Okay. So we're going to follow the rules proposed by Ron Howard. So he's one of the founders of decision analysis. In fact, he coined the term decision analysis when they were still calling it statistical decision theory or some other decision theory and things like that. He proposed that decision analysis is the best term for this field. So the 5 axioms we have are order rule, probability rule, equivalence rule, substitution rule, and choice rule. So let's go over them one by one. Okay. So the order rule or axiom says that a decision maker, when faced with deterministic outcomes, can rank them in the order of his or her preference, and ties are allowed. Okay. So, for example, if you have a decision maker that has 5 outcomes to choose from, right? A, B, C, D, and E. One of the ways they can rank them, let's say, is A is preferred to, so greater than, I'm using it as a preferred to sign here. So A is preferred to B, B and C are the same, C is preferred to D, and D is preferred to E. You don't have to have this order, but an order like this is always possible. That's the claim. Do you all agree or not agree?
Yes.
Yeah, generally there's really, I've never seen when I'm teaching this class that there is any disagreement here. People think, yeah, I can rank things in the order of my preference if ties are allowed, right? I'm not requiring you that you say that 2 things cannot be the same. 2 things can be the same to you. But what is not allowed is, let's see if I have, is cycles, right? You cannot say I prefer A to B and then I prefer B to A now. That's something you're not allowed to do. But if you say, and then this also applies to multi-attribute options. So let's say you're buying a car, and car has many attributes, right? It's not just cost, it's looks, it's acceleration, it's how much room it has, it's fuel economy. You can still say car A is better than car B, or car A and B are the same. Okay, that's the claim here. So, and then again, this room, since we're talking in this room, everybody should agree. And if you have any issues with any of the axioms, just let me know. Okay, so generally very easy to satisfy. People agree with it. I mean, I've typically seen that, when I teach this class or in any other setting, people don't have any problems with this rule. Money is an easy example, right? If I give you, say, you're getting this much money, which one do you prefer? Oh, yeah, of course. So, no problems here, right? Pets. Can you rank pets in the order of your preference?
Depends on each one of them's likeliness. Some people might like cats over dogs, and so on. So they might rank it in that order.
Right. So the point that is made is that people may have different rankings, and that is actually allowed. That is perfectly fine. So long as you agree that you can rank it, and she can rank it, and that person can rank it, it's all fine. Individually, you should be consistent. You should not have any cycles in your preference. So you can't say I prefer cat to dog, dog to horse, and horse to gecko, but also gecko to a dog. To the point that I was making earlier, that human beings are can act irrationally sometimes. They sometimes switch their order of preference, and then that's why we say we want to be normative. We're not trying to be descriptive like people sometimes make inconsistent decisions. This is a normative approach of making decisions. Anybody prefer a gecko here or no? Right. So, and then, like I said, you're allowed to rank them however you want. So there's no nobody can question why you're ranking it like this. All I'm going to say is that we will follow the sequence of mathematically consistent decisions, and we may reach a point where you disagree with what decision analysis said. Then I can track back and say, you know what? Now you're saying that you prefer this animal to that animal when initially you said you prefer that animal to this animal. That's how these things work. Okay. And humans are very good at ranking alternatives, right? So we've seen that in a lot of some research and other work that we do using decision analysis, we say that this is almost never an issue. Right? But deterministic outcomes. Once you have uncertainty, then all bets are off. Then they start getting. But then you basically have a systematic way of incorporating uncertainty anyway in decision analysis. Okay, so references must be transitive. Transitivity basically says that cycles are not allowed. You can't have something like this. Okay. So if everybody is able to rank things, then we can move on. Okay. So the next one is, by the way, this was an example of a bad choice. You can't do this. Okay. Because you're saying again that E is preferred to A. Now, the next one is, the rule states that the decision maker can assign a probability to an outcome based on their degree of belief. Any comments on this one? You had a comment, right?
Yes, sir.
Did you have a comment on this one?
No, sir. I was just thinking something.
Okay. Make sure you grab the mic before you say that, because this is the one that we sometimes have people raise concerns that, well, what if I don't really know? Let's say if I ask you about probability of failure of a system that I don't quite understand, or it's a really complex system that I don't know. So what about those cases?
That's why the degree of belief is so at that point in time, whatever you know, you will assign the problem.
Right. So the point that was made is that the degree of belief is, if you buy the degree of belief interpretation of probability, then this should not be an issue at all. And we already talked about many settings where it's infeasible to collect data, or you have limited data, and or your prior belief, you have some experience with the system. So you take your prior belief, combine that with data, and then you have a.
It's always iterative. This approach is iterative because the belief has to be updated with latest data.
Yes. So again, the point that has been made is that it's iterative. So yes, at this point in time, this is how much data I have, and this is how much my prior belief is. Based on my prior belief and data, this is my best model of probability. And then, based on that, I can assign a probability to an event. Tomorrow, in the next cycle of decision making, let's say, I will look at the data I have at that point, look at what I've learned, and I'll make a different decision at that point, or may make a different decision at that point, right? But at every stage of knowledge, I can assign a probability to an outcome based on my degree of belief. And if everybody agrees, then we all agree to this with this axiom. So degree of belief is formed by prior information and data. So again, people have argued that how can they assign probabilities to events that they have limited knowledge of, and then we again go back to our definition of probability as a degree of belief. And then I do a worked example that what is the probability the weight of a certain automobile is greater than 1800 kilograms? I point at let's say an SUV, and I say, what is the probability that that is over 1800 kilograms? Well, different levels of knowledge, right? So you could say, if we're totally oblivious, we don't know anything, we'll say 50%, just like we did in the earlier coin example. There's really no reason to believe higher or lower. But then you could say, you know what? I have looked at curb weights of a lot of cars, and I can tell that most SUVs are over 1800 kilograms. I'm just making this up. You can use your prior knowledge, and you can say, you know what? I'm going to say 80%. Then you can say, looking at the vehicle, and then you say whether it's a unibody, which is usually lighter, versus body on frame type vehicle, and you can make assessments. So you're using subjective knowledge to build a probability model. Another thing you can do is that look at product data sheet. And then, so basically you can resolve uncertainty as you go, and you can answer that question. You can assign a probability to this event very, very easily. I shouldn't say easily, but it's possible. So, and then I again reiterate, a decision made using a current state of knowledge can be a good decision if collecting further information is cost prohibitive or is precluded because of other reasons like time pressures. If we don't have time, I mean, I can come up with a hypothetical scenario, right? So you're going through, let's say, an intersection, and then it says weight limit on your vehicle is this, and you're already driving at a certain speed. What do? Right? So you say, okay, well, I guess I'll keep going because I think my vehicle is under 1800 kilograms or something like that. So just making that up. But those things can happen sometimes when you make a decision under severe time pressures. And in those cases, it's still a good decision if you fully used your knowledge of vehicles and so on and so forth. The next one, so looks like, I mean, there wasn't that much of a concern here, so we can keep moving. And I think that decision analysis axioms are important for everybody to agree, because we will build a math model based on this. Okay. So the equivalence rule states that a decision maker is indifferent between a sure outcome and an uncertain lottery involving best and worst outcomes for a certain probability distribution over the outcomes of the lottery selected by the decision maker. So it's a mouthful. So we'll parse it into small pieces. Okay, we'll say equivalence rule states that a decision maker is a sure outcome and an uncertain lottery. Roughly speaking, in most cases, if there's an uncertain decision and a sure decision, you can find equivalence by playing with the numbers of the lottery. Okay, whether you're changing the outcomes or the probabilities. Let's look at this a little bit more analytically. So, again, we consider 5 outcomes, A, B, C, D, and E, and they have that preference as shown. So, A is preferred to B, B and C are the same, C is preferred to D, and D is preferred to E. Now, let's say you're given a choice between sure outcome B and a lottery between options A, which is the best outcome. See, A is better than every other outcome here. And E is the worst outcome. So E is the absolute worst in that ranking that you saw. Okay? So it's important to distinguish that order rule by definition leads to this, right? If you have a bunch of outcomes, and you can say you can rank them, obviously there has to be one or multiple that are the best, and has to be one or multiple that are the worst. Okay? So just to add clarity to this, and this is not absolutely not required, let's talk about money so that we can at least understand this well. Okay? That A is worth $100, B is worth 10, while E is worth 0. Okay, this is just for clarity. We're not doing anything. We're not bound to using money in this case. So A is 100, B is 10. So of course A is better than B, and then E is worth 0. Okay, no problems there. Option 1 is you get B for sure. Okay, now you can see. Okay, option 1 is B for sure, and option 2 is some lottery between A and B. So this is important here, that here we put the best outcome, here we put the worst outcome. And then we have some probabilities here. So you already know that the circle means uncertainty, right? So if you go with A, you get $10, you go home. You go with B, some event happens which has a probability P, that, and then if it happens, then you get $100. If it doesn't happen, with probability 1 minus P, you get $0. Okay? The claim is that you can always provide a probability P that makes you indifferent between option 1 and option 2. Do you agree?
So P is point one and non-state point.
Yeah.
We are saying we are indifferent. And we consider P is point one and non-state point.
Okay, so we'll get back to that point. One of the point that was made is that P should be 0.1 and 1 minus P should be 0.9. And I think I can see the reasoning that you used here. Okay, we'll get back to that point. That is a very important point that I want to make regarding that. But at this point, let's just stick with the fact that P exists. Okay, and for each of you, it could be a different P. Okay, so obviously when P equals 1, what do you prefer? Right, that's trivial, right? Because you get $100 for sure. What happens when P equals 0? Option 1, right? So if P at 1, you prefer option 2, P at 0, you prefer option A, and somewhere between 0 and 1, you switched, right? We're just looking at the switching point. It has to exist. Right? There's no way around it. So, and you provide that number. That's all. I'm not even providing that. And it was possible because we started with the best and worst outcomes. So these two outcomes here have to contain this outcome. Otherwise, this logic doesn't hold, right? If this was $110, B was 110, there's no way you could do this, right? So you have to work with best and worst outcomes here, best and worst, and then this will always work. Okay. So, and sometimes we call it the preference probability associated with outcome B. So B is the intermediate outcome, and whatever probability we assign here, we call it the preference probability associated with outcome B. So you provide, like I said, you provide the value P that makes you indifferent between these two options, not me. Okay, so that gives the decision maker control over what this number should be. Okay, and a value of P between 0 and 1 must exist in this setup. The other point is that the preference probability P must lie strictly between 0 and 1 for intermediate outcomes, right? So A was preferred to B, and so on and so forth. For the intermediate outcomes, it has to be strictly between 0 and 1. It can't be 1, because now you're saying A and B are the same, right? So in this case, if you say the P equals 1 makes you indifferent, then you're saying B and A are the same, correct? 100% chance of getting A is the same as 100% chance of getting B. Well, that's not what you said earlier. Similarly, P equals 0 also doesn't make any sense, because that's what we're saying $10 is the same as $0. So you have to, so those that you're violating your own order rule. So basically you can look at your responses to order rule and see if your preference probability makes sense or not. Okay? So it's pretty straightforward concept, nothing really difficult here. Another thing that you can probably see here, there's 2 points I want to make here. One is that if this probability increases, does that mean that you value B more or you value B less? No, you're indifferent in option 1 and option 2, right? So larger value of P here means what? Does that mean that you value this outcome more or less? Another way to say this is, we go back to our
Based on the order of differences, it is less.
no, B is less, of course, right? So let me just go back a couple of slides now. Actually, this is a better slide to look at everything all at once. Okay, so I prefer A to B and B to C and D, and then B is the same as C, and then that to D, right? So let's say somebody gives me some indifference probability for B, Bravo, and then I ask them the preference probability for D, Delta. Would the preference probability of B be higher, or preference probability of D would be higher?
B is
What about preference probability for B and preference probability of C? It should be equal, right? So the preference probabilities follow the same order, because higher probability P means that you need a higher probability of the best outcome to give up this sure amount, right? So you value it more. If if B was like $1, you would say, you know what? Even at 0.2 P, I'll play the lottery because I don't value B as much, right? So that also shows as a barometer of how much you prefer a certain outcome. Okay, so that's one point I wanted to make. That the more you prefer something, the more the preference probability associated with that outcome would be. And the other thing is that this doesn't have to be money. That's very critical. You could do this with animals too, pets that you prefer, right? So if somebody preferred dogs to gecko, like dogs were the most preferred animals, and gecko was the least preferred animal, then on the left-hand side, I could put a cat and find the preference probability associated with it. No loss of accuracy. I could still do it, right? So you can compare qualitative options too, or complex options where you can't really put money amounts or things that is easy to calculate things in, right? So just keep that in mind, that these outcomes A, E, B could be anything, okay, that you prefer. Right, so if you buy that, then you have to also agree with substitution rule, right? No, rather, we already did the equivalence rule. Substitution rule, basically, or axiom says, then equivalence has been established. You establish equivalence, you said, for this, sure B and lottery between A and E, this probability makes me indifferent. Great. Everybody understands that these are hypothetical probabilities, right? These are just you assign probabilities, that if that probability existed, then I would be indifferent. Then substitution says that you should be happy to substitute one with the other, right? So if you say that a sure outcome and a lottery between the best outcomes, you found equivalency between those, then you should be indifferent when one is replaced with the other. You shouldn't care. You said you're indifferent, right? Thank you so much.